think. No, it's spinning. Oh, okay, it's going. It's going. Do you guys want to go over a couple more of like just like what's the inverse blah of blah, or do you or
No.
go over one or two? One?
No.
No? Okay. The last couple of questions, I had holding the wrong thing. The last couple of questions ask you, I remember the question. It goes, for any positive number m, for any number m, sorry. If you want some fancy symbols, you could say for all, yes you do, because of the Taylor, for all m in, or for all positive m values at least. Is that fancy? Look at that, it's a fancy symbol. It means for all.
Same as,
Same as what?
it's just an upside down A.
Yeah, isn't that neato?
Okay.
This means there exists.
If you turn it upside.
Yeah, that looks cool.
Isn't that cool? So in math, so to compact certain sentences, you can say, oh, there exists an x value that has this property, or for all x values, this must be true. This must be true. This says for all positive numbers you can come up with, it is true that the inverse tangent of that number plus the inverse tangent of the reciprocal of that number is always going to equal a certain number, a certain value. And so it says, the question asks you to figure out, this is the third to last question. The question says, hint, draw a right triangle. Okay. Sweet. In fact, actually kind of, just to make a certain point here, I might draw it like this. You don't have to redraw it, it's fine. Because the point is, this is some angle, right? What if I wanted to talk about this? What if I wanted to describe this angle as the inverse tangent of some number? Keeping in mind that this statement is equivalent to saying the tangent of that angle is m. If you think back to the first couple of problems in our problem set, okay? For example, just a quick example. If I said, oh, the tangent of some angle is 3. How do you draw that? Well, yes?
Mm-hmm.
So then I could say, well, that angle, I could describe that angle as the inverse tangent of 3. Right? Okay. So, how do I label this triangle then?
M1, and then one's on the left.
M and a 1. So, if M was like 10, it would be really tall and not very wide, right? But M could also be a number like 2/3 or 1/5, right? M could be any number. Does that make sense? Any positive number.
Mm-hmm.
Based on how much I shrink that? Shrinky dinky? Yes. Okay, so how about this? This also describes an angle. Where do you see an angle whose tangent is 1/m? Right there. You see what I'm talking about?
Mm-hmm.
So for this angle, I could say, well, the tangent, is 1/m. Now in this angle, the tangent value is m/1. So when I say this plus this, I'm basically talking about this angle plus this angle, aren't I?
90.
What are they? They add to 90, but we've been talking about radians the whole time, so 5/2.
Yeah.
You guys all see why those have to add up to 90?
Wait a minute. Can you back up a little bit?
Yeah.
Wait. Just a little
I mean physically?
No.
Yes.
No.
So do you agree that this angle is described by this expression?
Oh, yes.
And then do you agree that this angle is described by this expression? And then the angles of a triangle have to add up to 180, right?
Right.
Or if you're in the angles of a triangle have to add up to 180. So if this one's 90, then these guys have to add up to 90.
Right. Okay.
And so- So this is just depending on what framework you're working in. Like for example, let me give you a quick calculator example. If I take my calculator and I say, okay, what's the inverse tangent of 7 plus the inverse tangent of 1/7? And I take my calculator and I put it on degree mode, There's the mode button. Okay, it's on degree mode. What's the calculator going to tell me? You'll have to take my word for it. Here's the actually the answer to this. Will it give me 90 or will it give me like 89.999999 or something really close?
Really cool.
90.
It actually comes out exactly 90. It shows you how sophisticated the programming is on here. Because like this number, because look, like the inverse tangent of $7 million. Someone can guess this angle to the nearest millionth.
29.27742.
No, bro. 7. If your triangle was a 7 and a 1, this angle would be like pretty fat,
Yeah.
right? Anyway, so this angle is 81.869897 degrees, and this angle, if I type in inverse tangent 1/7, is roughly 8.130103, whatever. And it just so happens, well, it doesn't just so happen, but those add up to 90. What's kind of cool is the calculator. Sometimes with computers, they'll have certain like little floating point issues where they try to add it up and you get like, oh, it added up to 90.00000006 or something weird like that. Anyway, I'll shut up. Let's move on to the next one. Anyway, if I put my calculator on radian mode, it would have spit out half a pi, roughly 1.5 something or other. Okay. What if one day they determine that this is like psychological abuse and I'm like put on for like crimes against humanity? Yeah. Any of you guys defend me at my trial?
Yeah.
No,
Depends on what
Serena would
they-
come out. What's the opposite of a character witness? Like a character assassination witness. They come and just go, this is a horrible man. You should be put behind bars.
Made me do math.
Following order.
Yeah.
I was just following orders.
Interesting. Was that defense successful for any of those defendants? It was unsuccessful across the board, right?
Yeah.
Not even the low level guys were able to use that.
Everyone who was tried at the Nuremberg thing were people who had like
So
100 people could say, oh yeah, I watched him kill this dude's entire family.
yeah.
It's always interesting to read about like Werner von Braun, who like was a genius, but like a pretty bad man. But the U.S. was kind of like, well, he's so good, we gotta just put him on our team.
Oh, now I remember where I heard that name. He did something for like the space race.
He invented the rocket.
Yeah.
basically, yeah. He made.
Switch teams.
He's arguably the father of all like modern, space travel.
Yeah, I know his name.
He's not.
No. It's actually a Nazi. You're pretty
Bold word
close.
Yeah. He was not good guy, but anyway, sorry. There's another problem on here that's where it's like a 5x5 triangle. I'm gonna try my best to draw it here for you.
Yeah.
You should have a grid, right?
Yeah.
Okay. So first order of business. There's a hint on here. I know it's kind of hard to write this question because I wanted you to look for this really nifty. Hello.
Give me the paper.
Zarita.
What?
No.
Says, you're expelled.
Now goodbye.
It just pick it up between classes. Office. Something like that.
Are you sure it says that?
I'm pretty sure it
It says you were
It
expelled.
would be cooler.
You have 10 detentions.
Leave the
Okay.
school.
So the clue gives you this hint of like, look at the connection between this angle, and this angle. Okay? Can you put that? Thank you. Thank you very much for your cooperation. Okay. So suppose I labeled these angles like A, B, and C. How would you talk about angle A. How would you talk about angle A if you were kind of forcing yourself to think about tangents? What's the tangent of angle A?
One.
1. Great.
Yeah.
So I can then say
Inverse tangent of one.
the inverse tangent of 1 tells me what angle A would be. Now, it's not shocking that that angle is 45 degrees. We know that. Right? Pi over 4 radians. So then, look at this triangle. Do you notice anything about this region here?
That seems awfully like a 90-degree angle. or something.
Seems that way. How do you know for sure that it's 90?
You
You
find the
believe.
slopes of the lines that are
Yeah,
next
they
to it.
have
Yeah.
opposite slopes.
What's the slope of this guy?
It's like negative 1/2.
Yeah. So if you have some slops
Negative 1/2.
of negative 1/2
And 2/1.
and positive 2/1, that tells you that they are perpendicular. Right? Cool beans? Okay, so that's one thing done. Okay, great. It's a right triangle. That means I can easily talk about tangents. So how does this length here, that long leg, compare to that leg? Again, I'm talking about angle B. So if the tangent of angle B,
Over tangent.
did you actually calculate them?
Yeah,
Yeah, how long is this one?
5√2.
Is it?
I believe so.
I don't
Isn't that
think
the
so.
other one?
No, hold on.
That's this one. This one's 5/2.
The short one's root 5.
Yeah, the short one is √5. And this one's
This one would be 3 root 5.
Because
Well,
that's
if
the
you-
5.
well-
That's fine.
Yeah.
If you calculate this, well, to go from here to here, how far over do you have to go and how far down do you have to go?
Over 6, down 3.
Over 6, down 3. So if I call that, if I do a quick Pythagorean theorem, 45, and 45 is 3 root 5. You understand what I'm talking about?
Yeah.
No. Here's the thing though, did you really need to find its length?
No.
No, we're all about ratios, right? So if you just look at the fact that this segment is up 2/1, and this segment is up 1/2, up 1/2, up 1/2, 3 times. Does this make any sense?
Yeah.
Do you see how this must be 3 times longer than this? So therefore, what's the tangent of angle B?
3.
3. You understand?
Yeah.
Okay, so what does that tell me? That tells me that the inverse tangent of 3 tells me what angle B is. And that's the hardest one to really to figure out. How about angle C?
2.
The tangent of angle C, that makes sense to everyone, right? Why it's 2?
Yeah.
Opposite over adjacent. Okay. So, now, if you like niftiness, which I hope you do. You do, right?
I'm a big fan.
I don't know, man.
You gotta be a fan of niftiness. It's nifty. What does this tell us? It's a crazy identity. No? The inverse tangent of 1 plus the inverse tangent of 2 plus the inverse tangent of 3 equals
180 degrees or 5.
Wow.
Isn't that wacky?
Whoa. That's a little wacky.
No, what's crazy is if you look at the decimals separately, like, I'm gonna go back to radian mode. My Mr. Quackmulator. I don't know, it's kind of neat. Like this guy here, the inverse tangent of 1 is 0.785, blah, blah, blah. The inverse tangent of 2 is 1.107, blah, blah, blah. And the inverse tangent of 3 is 1.249, blah, blah, blah. And just remarkably, they all add up to exactly pi. Isn't that's lovely?
What is that? How do we do that?
Sorry, I thought it was interesting. Okay, let's look at the last one. Okay.
Wait, where did the name for pi come from?
Greeks.
Just
They
like
like
a-
Oh, pi is a letter of the Greek alphabet.
Oh.
So I don't know why the Greeks obviously had a fascination with math and numbers and especially geometry.
Yeah, because they had a religion about it.
Yeah. Pythagoras had like a whole like cult. Couldn't eat beans. No beans. Beans bad.
But how do you do analogies then?
What?
Because you use beans as an analogy for someone a lot of times when you're like, you're a bean, you only know one thing.
Yeah. I don't know. Pythagoras didn't like beans. Like, they didn't eat beans. Pythagoras. His followers. No, but yeah, so like pi, when they notice that, yeah, a circle, you make a circle, like you take a piece of string, you draw a circle in the sand or whatever, on paper. You go, oh, the length, the distance around that circle is exactly, pi times bigger than the diameter. You had to assign it a symbol. I don't know why they use p. I think pi is p in the Greek alphabet. Although, you know what this symbol is?
Hmm.
Kind of annoying. This is p and this is rho. And you're like, bro, why?
Bro, why
Oh,
P-Row?
yeah, they don't.
This is rho in the Greek alphabet, lowercase rho. But it looks like a P.
What's up
Yeah.
with this row?
Huh?
Is it just a bigger?
I can't remember. I think it just looks like an R, but I'm not sure actually. Here, I'll Google it for you. Just for you, Alyssa. Just for you. No, rho looks like this. Wait, maybe rho is the P. What's the pi then? Hold on. Sorry, give me a second. I know there's not like an exact 1-to-1. No, yeah, because it goes nu xi omicron pi lm. Although where is xi? It's not an exact 1-to-1 with our alphabet, so I don't know. Ask someone who knows more than me. I just know them because they come up in mathematics. Like rho is that letter. They use rho for like the radius in a spherical coordinate system. You want to determine where something is in three-dimensional space and use like spherical coordinates.
Ah, cool, spear.
You do that? Really? Oh. Well, if you're talking about locating something in three-dimensional space, you can go X, Y, Z, and that'll get you there.
Oh.
Or you can make like a globe and go. You can go rho for the radius, and then you talk about these angles phi and theta. So you can use two angles and a distance to say where something is in three-dimensional space.
Oh, I actually did hear something about that.
Our GPS is a bit like this. Phi is kind of like latitude, and theta is kind of like longitude. And then rho, well, the Earth is roughly a sphere, so rho is just always the same number. But if you could go up and down, that would be like your elevation.
Man, what if the Earth was a cube?
Okay, let's do the last one. The last one looks. Can I see your diagram? Did you answer it correctly? Did you get it?
I believe so.
The last question, guys. And if you guys want, we can go over some. If you have any more questions about this stuff, but hopefully you're.
Can we go over 116?
Of course.
No, it's not.
Okay, I try my best. So, this question asks you to focus your attention on this angle, and this angle. So for this first one, if I'm gonna write him, it asks us first to look at inverse tangents. If I go inverse tangent of, what's the ratio between this and this?
1 and 2.
It's a 1 and a 2?
Yeah.
So the inverse tangent of 1/2, right? So this, are there any questions on this, guys? This describes that angle.
Yeah.
The one with a single arc. We sure that makes sense? Yeah. This guy would be the inverse tangent of,
Oh,
how do those compare?
1. Oh, they're the same.
Are these the same length?
Yes.
They'd both be root 5, wouldn't they?
Wait.
Yes.
Yes.
It's
Yes,
a 1 by
they
2?
what?
Yeah.
Yeah.
Well, Pythagorean theorem, right? 1 squared plus 2 squared.
Oh.
You can use the same argument over here. If you look at the grid, it's a 2 by 1 triangle here.
Right, gotcha. Okay.
And then, so the inverse tangent here is 1. So that describes the middle angle. And then the third one, how big are these?
1 and 3.
1 and 3. So while we're at it, how big is this?
Square root of 10.
10. Are we okay with that?
Mm-hmm.
So this guy has an inverse tangent of, or the angle has a tangent of 1/3, so I can describe the angle as the inverse tangent of 1/3. Does that make sense?
Yes.
And so that equals 1/2 pi. Now you don't have to do this, but it's prettier if you write it like this, I think. It's kind of neat. Right? Isn't that lovely? Sorry. I'll try to come up with a better problem next time.
I'm just gonna look at you disappointed.
I'm so disappointed. I am there's an ancient image. Remind me, son, I am disappointed. That was a good one from before you guys were. Huh? Do you know that one?
Are you winning some?
Are you winning, son? That's a good one too. Okay, so then the other one is, it says, okay, do it for the inverse tangents. What about the inverse sines? Can we get a similar statement? Let's do the same thing. Sorry, not tangent, my bad, guys. Inverse, I did say sine, right?
Yeah.
So this angle, instead of talking about this angle as the inverse tangent of 1/2, right? I could talk about this guy as the inverse tangent of, the inverse sine, of 1/√5. This one's not gonna be quite as pretty, but it still is neat. How about this one? He's the inverse sine of, yeah, this over this, but √5 over √10 can be simplified, right? As 1/√2, right?
Mm-hmm.
And then the last one could be written as the inverse sine of 1/√10. And when you add those up, it's the same result as before. It's the exact same thing. So, sure, there's a lot of interesting things going on here, I think. Like for example, the fact that this number times this number is this number, not the inverse sines, but the number inside. 1/√5 times 1/√2 is 1/10. Whereas that relationship's not happening here, but anyway, kind of neat.
Mm-hmm.
Which number did you want to go over? Someone asked to see about one of the other ones, right?
Yeah, can we do, which one? Yeah, can we do K on 16?
Sure. Can you tell me what it's asking?
Inverse secant of -2.
No, that's not the inverse, it's just secant. Wait, we're on 16, right?
Oh, 16, I'm looking at 17.
Secant of
Secant
11.
11 pi over 6.
Sorry, I went on the page.
No problem. That's the one you want to do, though, right? This one?
Yeah.
Okay, so step 1 is locate the position. where do we locate the position? Or, I don't know why I said it that way, but how do we locate the position? You think about chopping it up. A fast way to think about this is awfully close to a full 2 pi, right?
Yeah.
It's a sixth of the way, so almost all the way around, we're just a sixth of a pi away from a full circle. So there's my triangle. Notice the x, the horizontal is the long, and the vertical is the short. Notice also that the horizontal is positive and the vertical is negative. How long is the horizontal going to be?
Root 3 over 2.
I agree with the root 3 over 2 part, but that's a positive. Now, I don't even really need the y value, but I don't know. I think it helps reinforce what you're doing if you just, once you're a pro, you.
Negative.
Thank you. Yeah, good. What I was saying is, once you're really proficient, you might just do all this in your head or just a quick little jot down. But like, it's good. It'll help you remember things and memorize the spatial relationships if you just kind of draw the whole triangle. But anyways, everyone okay with why that's where he lives? Okay, so according to this, the cosine of 11 pi over 6 is positive root 3 over 2, right? The x value. So the secant is the reciprocal. And that's a totally fine number. However, you might see that get written like this. If they want us to put it in simplest radical form or have a rational denominator and convert it.
Yeah.
Do you guys want to go over an inverse one? Or do we feel anyone else? Don't be shy.
17J.
Of course, Rita. Of course. What does it ask you?
No, it's the same thing.
Inverse cosecant.
Except negative.
It's fine.
Inverse cosecant of negative 2 root 3 over 2.
Okay.
7.
Yeah, so Nikita, you're right. There's a connection here between this and this.
But negative.
Because when you see this, what I hope you do, there's kind of a, first thing is you go like this. You say, well, this is saying that the cosecant of my angle is this weird number, right? And that's equivalent to saying that the sine of my angle is the reciprocal of this number. Now, when you first write that down, my goodness, crinkly, crinkly.
I can't figure it out, man.
We've lost our clinical privileges.
That number might not immediately make sense. Like, wait, I don't recognize that guy. He looks kind of familiar, but the thing is, if you multiply this by root 3 over root 3, or if you just understand that 3 divided by root 3 is root 3, you can simplify it to this. Do we understand?
Mm-hmm.
So now, where do I go in my unit circle so that my sine value is, firstly, how do I get a negative sign? Do I want to be up here or down here? Down here. And this is going to be my y value. So my triangle has to be, is my dot going to be closer to the y or the x axis? It's going to be closer to the y axis because my long side is going to be this, is the vertical. Make sense? So that's what my triangle looks like that. Still, is this making sense?
Mm-hmm.
Now, how do I describe that angle? This, I said this before, but I think this is one of the trickier parts of this process, is understanding why an answer 5 pi over 3 is not quite correct. It's negative pi over 3 is the answer. And that part can be confusing because you're like, well, wait a second. Doesn't 5 pi over 3 produce that sine value that I want? And the answer is yeah, but with the whole, when you're doing an inverse function, you're restricting yourself to outputs between negative pi over 2 and positive. However, if you put 5 pi over 3, I'd be like, it's barely wrong. All right.
Thank you.
Pardon the interruption. This is Mr. Bowman. Somebody dropped off a picture envelope in my office earlier